welcome everyone. Today, our colloquial speaker is our own TC, Chian-Chou. Just very briefly, TC is an alumni of NTU Physics. He got his PhD in the University of Hawaii at 2013, and after postdocs at Durham, and also ESO at Garhi. He joined ASIAA as an assistant research fellow in 2019. And today he's going to tell us about dusty galaxies. Let's welcome TC.
Hi, it's great to be back in this room. I think last time I gave a talk, colloquium is my job interview. So that was 5 years ago, roughly. And then, can you hear me back? That's what Alex told me. I listened to your talk. So I'm actually in the process of applying for tenure, and I don't think there's a thing called tenure talk here in the IA, but I thought, 5 years is a good time to summarize what I've done and essentially give an overview and also maybe a plan for the future so people expect what I'm doing in the next few years. Along this process, 5 years, a lot of collaborators. Wei Hao obviously is my senpai, Shixiong. And Fabrizio, you probably met him. He visited a while back, long-time collaborators, and a few others that I've been keeping in long-term collaborations. And some of the work, most of the work are actually done with them. In the past 5 years, there's a number of papers published, but I mean, I cannot condense all this into one talk here. So I mean, if you are my students, and if you don't see your work flashed, please don't hate me. I try my best, okay? All right, one of the things I think is most different if you're a postdoc student is that when you're faculty, right, you get to work with talented students, and you don't get to do that when you're postdocs. And that's one of the biggest difference in terms of your research life, being a postdoc and being faculty. And I think I'm most fortunate to work with a lot of students in the past few years. I want to thank them for their courage, actually, to choose me as their supervisor, because when I started, I had no ideas how to become a supervisor. And so, they are very courageous. So, and things seem to work out well, so I hope I'm not a terrible supervisor in that sense. So, quiz. Raise your hands if you know what this image is about. Our juniors. The seniors don't count, juniors. CMB, yes, here's your snack. Here we go. Here for dose of dopamine here. It's a CMB. I have more to come, so pay attention to the talks. You're gonna get some gifts. This is CMB, cosmic microwave background. Everybody knows. So I guess, I'm not sure if you know, background light actually have different, every wavelength there's a background light, from radio all the way to gamma ray. And CMB is most well known because it's the first thing to be detected because it's the brightest, right? And this is like 10 orders of magnitudes in flux densities, and this is the frequency, right? So this is the first thing to be discovered, but then as we improve our technology, we discover many other background lights, different wavebands. I called it a CD of the universe's spectral energy distributions. As it turns out, different wavebands give you very different information and constraints astronomical phenomenon very importantly. They are fundamental, right? This is absolutely true. Wherever you look at, these are the background light, this is how much the energy is. So for radio, X-ray, and gamma ray, we know that they constrain black hole growth, AGN. For CMB, we know that they constrain primordial emissions from the Big Bang. And then for optical and UV, they provide information about stars. For my interest is the CIB, is the infrared background. It's mostly coming out from the dust obscuration, the stellar lights, and reemitted to the infrared. One of the reasons I'm interested in the infrared background is that it's one of the most challenging background to measure because it's hard to measure from the ground. This is the frequency that, if you remember, this essentially the atmosphere is opaque. There's only a few windows that you can observe, which is why the CIB was not very well constrained, and the absolute level was not very well constrained that way. In any case, people still try to assess the energy density of the infrared background, and they found is the numbers here are energy densities. Obviously, CMB is very bright, but then CIB is comparable to the optical background. So that just tells you that if you want to study galaxies, you need to combine optical and infrared to get the full picture of the galaxy formation. Here's a very good example recently from JWST. On the left hand, it's the same galaxy. On the left hand side, you have the optical imaging, and the right hand side is near infrared. You see where you have this dust lens that's obscure. You don't see that in optical, but it's very bright spiral arms in the infrared. So the two observations are highly complementary. I just want to drive that point home. Scale back a little bit. If you do census of galaxies and you look at where star formation occurs, this plot shows you this is the star formation rate density, the volume averaged, and the orange ones are the ones that's sitting in the dust obscure regions, the star forming regions that dust obscure. And the blue ones are not as obscure. This is redshifts. I mean, it's kind of misleading, but at redshift 2, it's about 80% of the cosmic time. Right? So the majority of the cosmic time, the stars are born in dust obscure regions in galaxies. It's highly uncertain at high redshifts, but just to give you an example that, recent discovery at redshift 8, that's about 5% of the cosmic time. You already have a lot of dust. This is showing the contour in one of the dusty galaxies at redshift 8. So a lot of effort has been trying to put constraints on this high Z tail, but I wouldn't be surprised that if the dust is dominant, also play an important role at higher redshifts for star formation. Dusty galaxies, not only very important for understanding star formation, they're also important are linking to different various galaxy population that you see across cosmic time. This is a big bang, and it goes to the age, go to the present day here. The elliptical galaxies and compact galaxies, merging galaxies, quasars, and dusty galaxies, they are proposed to be linked. They're also proposed to be linked maybe to the galaxy that's recently been discovered in JWST. They are the most massive galaxies at redshift 6 and above, the epoch realizations. And based on the clustering measurements, halo mass, what you want to remember is that they could be also progenitors of the descendants, obviously, for the galaxy at the epoch realizations. So they are linked into a wide range of galaxy populations. They play an important role in the galaxy evolution. And then I'll be focusing on, obviously, this dusty galaxy phase, in particular, exactly how the star formation trigger that will be addressed in this talk. Try to understand how they get so much of star formation rate at a very short period of time. Okay. So, in this talk, I'll address 3 questions. I mean, the last one is not really a question, it's just a plan. Mainly 2 questions. The first is about cosmology. It's what's the origin of the infrared background? And are they galaxies or are they something else? I try to design surveys, observations to address that. The second question is about galaxy formation. Exactly, the question I want to ask is like I said, why does the galaxy have so much star formation rates? You don't see that in local universe. What triggers the star formation? And the third one is my plan. Okay? So how do you measure extragalactic background lights? There are 2 ways. The first way is to call the light buckets. So you have very small aperture of telescopes. You observe the whole sky, and you collect all the light intensities, and then that's it. You have the upper limit of the total energy density. I mean, there are some wavelengths you can do this, but not all the wavelengths you can do this. So there's also another way that's using a so-called bottom-up. You do surveys, you count galaxies, right? And these galaxies are seen as backgrounds. They are not within Milky Way. They are the backgrounds. So essentially, you just add the energy density of these galaxies, add it up, and you got the total energy contributions from galaxies, right? So ideally, if the background is contributed by galaxy only, the 2 approaches should meet, right, at the central grounds. They should meet somewhere in there. They should agree. The measurement you measure from the light bucket should agree with the measurement that you integrate from the sources, the discrete sources. In reality, this is very quickly schematic pictures of how you do it. You have a survey of effective area, you discover sources, and you plot essentially number counts, right? How many bright sources per flux bins, and so on and so forth. You put errors, and then you integrate, you fit a function, right? Integrate the function. Anything that's below that is the total energy of the discrete sources. And what you did is that you plot the total energy density. Now the y-axis is the cumulative energy density as a function of go to the fainter fluxes. This is usually what you get, right? You go to fainter sources, you see more sources. Fainter fluxes, you see more sources, so you got more total energy densities. And you try to do that compared to the light buckets that you measure from the satellites. And that's the approach I'm trying to use to understand the origin of the infrared background. There's been a lot of efforts. I won't have time to go through all the surveys, starting from the late 90s, I think. I'm just going to flash one of the most recent efforts that from IAA, essentially led by Wei Hao. It's called Studies. It's a scuba ultra deep survey in 450 micron mainly and 850 micron. So it does these two wavelengths that you can actually observe from the ground. We focus on 450 micron because 450 micron is closer to the peak of the infrared background line. And it's also less affected by the subtraction of the CMB. So the background line measured there is more close to the total infrared background. So the survey is already completed. It's almost 500 hours in total. There's a lot of time for Scuba 2. But the first confusion limited surveys is area and the depth of the survey. This is deeper when we go upwards, right? There's different surveys here. And Studies, one of the widest and one of the deepest. And it's hitting the confusion limit. Confusion limit means that this is the limit at which point is that no matter how much time you add to the images won't go any deeper because your noise is dominated by real sources, not background anymore. So that's called confusion. So this is essentially as deep as you can get with Scuba 2, right? Okay. With this amazing depth, how much of the background light has been resolved in discrete sources? The answer is about 40%. So this is the plot I show you. This is the integrated energy density as a function of the fluxes, and this horizontal bar is the background light measure from the buckets, right? So if you fully resolve the background light, you will hit the 100% mark. But then in the study surveys, this is the lines where the solid lines ends with the limit of the surveys, which is about 2 milliJNSky. So if you do that, corresponds to about 40%. It's done by Zheng Kai, sitting in the back. And then, obviously, there's a huge improvement here is that we don't know, how much of the light actually coming also from the fainter sources. Okay. So we need to bypass that because we cannot go any deeper in the images. So how? All right, raise your hands if you know how. How do I go deeper when it counts? With the blank fields that it's already hitting the confusion limits. Bigger telescope, yeah, that's one way, but we don't have that. We have to live with the Scuba 2. Sorry, the same telescope. That's a good thought. Anyone? All right, go ahead.
Prior detection.
What?
Prior detection.
Prior detection is one way. Yeah, you do stacking. All right, you got that. Yeah, you got the cookie. But I'm actually getting into another direction. Anyone? Change the wavelengths. That's also another good idea because then you go to the shorter wavelengths, then you decrease the confusion limits. Oh, there we go. All right, so it's good. All right, they are all good answers. Obviously, I didn't design the questions right, but the thing I'm trying to get is gravitational lensing. So, we know lensing. Lensing amplifies the background sources to brighter levels. So if you target your telescope on the massive cluster lensing fields, the very faint sources in the background is going to be amplified, right? So it can become detectable. Obviously, you need to do some tricks and modeling to get it back to the intrinsic fluxes, but that's doable, right? So that's the trick. So we've been leading sort of surveys and targeting a sort of sample of 10 clusters, massive clusters. And it's about 300 hours. But I mean, this is much less than what studies has. Studies has 500 hours. So we have limited amount of time. But thanks to the Hawaii collaborators, we're able to achieve this. So here's the image. It's led by Qining, one of my PhD students. And then you see this beautiful spectral image, and you see these white contours. These are magnification factors. So magnification to 5, 6, 10, or 2, things like that. So you have sources that's being highly magnified. So you know that you have sources that's fainter, 5 or 10 times deeper than that. So again, we build number counts. This is number counts. And then this is the previous, if you remember, this 2 milli-Jansky level that's reached by the confusion limit. And we're able to probe 10 times deeper because of the lensing. Okay. So it's the magic of lensing. You spend less time, but then you got to go 10 times deeper. So you're using the nature telescope for this. Lo and behold, with this flux density, we almost reached to about 1 milli-Jansky, 0.1 milli-Jansky, 450 micron. And then if you integrate that number counts to 0.1 milli-Jansky, you reach the full level of the background line. Okay. So for the first time, we kind of solved the problem. The CIB is mostly dominated by galaxies. So back to this question, can galaxies account for all the background lights? Yes, but I mean, measurements always have errors, right? So we estimate our errors about 15%. So to within 15% of error margin, we conclude that galaxies dominate and contribute all the background lights in infrared. All right, the first part is done. You're all following. Good. So let's move on to the next one. Now we know these discrete sources. We want to know the nature of them, right? What are they? So the thing we know is that they are very infrared bright. This is the typical SCD of the dusty galaxies. This is the optical UV and infrared and radial. The total luminosity is normally 10 to the 12 and above. If you know galaxies, these are ultra-luminous infrared galaxies, or lurks and U-lurks. They're very dusty. You don't have a lot of light coming out from the optical. Most of the lights are obscured by dust and remitted to the far infrared. That's what the SCD looks like. And in terms of redshifts, this is the redshift distribution of the dusty galaxies. They're predominantly located at so-called the cosmic noon. So cosmic noon means that there's a peak of the cosmic star formation densities right here, and the distribution of dusty galaxy match the distribution of the total star formation density pretty well. There's some facts you just remember that, and they're very massive. Their stellar mass is potentially 11, so that's 10 times more than the Milky Way. So these are the most massive galaxies you can get, and the most active in star formation rate you can get. So these are hundreds to thousands solar mass per year. You don't see that in local universe. Okay. What's the biggest problem of dusty galaxies? Anyone? Extinction. Yeah, I mean, they have a lot of extinction, so it makes them hard to observe in optical, that's right. But the physical reason why they have problems is this one's a bit difficult. Less gas? No, there are a lot of gas. I think that's actually the problem. There are a lot of dust, a lot of gas. So dusty galaxies are actually troublemakers for models. I've known a bunch of theorists. This is what they told me. We need to make very massive galaxies. They are realistic physical properties. They're very bright, very dusty, very gas-rich. And someone just gave up. Only God can make SMGs, dusty galaxies, in models. Let me drive that home a little. TNG simulation is one of the most upfront simulation, hydrodynamic simulation for galaxies. This is the number counts they try to reproduce. So number count, I showed that before, right? And then these are observation dots. And the two lines are, one's illustrious TNG, is the so-called the next generation. And the blue one is the original TNG. So you see that the next generation TNG actually doesn't work that well, compared to the previous ones, in terms of number counts, predicting the number density of dusty galaxies. The previous version of the hydro actually works better. However, the redshift distribution of the dusty galaxy, I mean, the original version completely failed. So the observation is about redshift 2 to 3, right? So the original illustrious, which is the orange here, if you sit in the back, it's about redshift 1. So it's completely off. So the original simulation matched the number density, but they are way off in redshift distributions. Whereas the new generations, they fit to the redshift distribution, but they are way off in number densities. It's also illustrated here is a more general galaxy population type of the simulations. The stellar mass star formation rate is called the Mann sequence. Illustrious TNGs don't have a lot of massive galaxies that have a lot of star formation rates. It just doesn't work like that, just in the simulations. So there's something also to know that for people who like to use illustrious DNG for comparisons, there's something you need to know is that that model doesn't work for massive galaxies at all. Okay. So how do we resolve this? From making a model to fit the observed number counts. There are various ways. Essentially, what you try to do is that you play with the initial mass functions. Given star formation rates, you put in more star formation into massive stars. So you make more dust, so that will boost the predicted galaxy to y-axis. So you have more fluxes for galaxy, right? So you play with IMF. The other is the same idea. You play with the dust attenuation curves. Essentially, you just try to make the curve move than the y-axis. You have more dust emissions coming out from galaxies. The third one is the thing I'm going to talk about today, is that you actually make more active galaxies. You move the things, sorry, I said it wrong. The previous two ones are moving things to the x-axis. And the third one is to make more galaxies that are active, so moving to the y-axis. So that's the trigger mechanisms of star formation. Locally, to make ULERGs, you essentially have to smash galaxy together. Because galaxy, when they form, they need fields. So you have to essentially get them a lot of fields to form a lot of gas and stars. And simulation does prove that. This is the sequence of galaxy mergers, is one of the examples of a local merger. And this is the time and of the merger process. So then this is the separation between the two encounters. You can see that as the galaxy goes close to each other, their star formation rates are boosted. And their star formation are most boosted by a factor of 10 to hundreds when they merge in the final stage of coalescence. That's when dynamical frictions make the gas go into the center, the funnels that make the density high and boom, like fireworks. The problem is that there are too few of the major mergers in high redshifts, so they cannot account for all the dusty galaxies we see. However, the universe is funny. They don't give you a lot of mergers. They give you a lot of gas, right? In the local universe, as you see in this plot from Tacconi, this is the gas fraction on the y-axis. It's the amount of gas per unit stellar mass. You have a lot more gas at higher redshifts compared to the local universe. What that does is that it shows in the simulation here. On the left hand is gas poor, on the right hand side is gas rich. When gas-rich galaxies, when you have a lot of gas, the gas start to fragment. And these clumps start to form a lot of stars. So in essence, you don't need to collide galaxies to make a lot of stars. You just make them a lot of gas, a lot of fields. They will just collapse in clumps. It's like star forming regions when you have a lot of gas. It's just clump fragments and make a lot of star formation. It's also seen in the simulations, the same simulation that do galaxy mergers. When they pull a lot of gas in, you see the gas start to fragment. So before they even merge or they are doing their own thing, the star formation rate here is already hundreds. Not thousands, but it's already hundreds. So before they merge, when they're sitting on their own, rotating, fragmenting, they're already making a lot of stars. And obviously when they merge, they boost their star formation rate, but not 100 times more. There may be a factor of few. That's what happens to galaxies when we put a lot of gas in them. So dusky galaxies could actually, gas-rich dusky galaxy could actually make a lot of stars, high star formation rates. The good news is that there are more dusky galaxies in high redshifts compared to mergers. Okay? So in essence, to solve this question, too many, too bright, too massive, I think one of the keys is maybe boil them down to how the star formation rate triggers. I'm going to do two approaches. One is to use ALMA to study gas fraction and thus the depletion time. I'll come back to that why And obviously, the second one is to use JWST to study their morphology. So why does gas fraction and gas depletion time give a sense about the trigger mechanism of star formation? So this is a survey of molecular gas that's done by Linda Tacconi and a lot of galaxy element sequence. So things on the main sequence, they are not very dusty. They are just normal galaxies. And what Tacconi found is that the depletion time goes down. It's proportional to the dynamical time. We know the galaxy dynamical time decreases as a function of redshifts. They go to high redshifts. The dynamical time goes down. And that's what you see in depletion time for galaxies. Depletion time means that the amount of gas, the time scale that you consume all the amount of gas given your star formation rates. That's called the depletion time. And also, on the main sequence itself, the more gas-rich galaxies, they form stars more efficient. In a way, it's a power law of 0.5. Okay. I know it's boring, but what it means is that essentially this fits into the distance stability. So for people who don't do galaxies, what you need to remember is that the observed correlations from main sequence galaxies, they agree with the predictions from distance stabilities. So they're supported by that. The question is, do dusty galaxies fit into these correlations? Right? Essentially, now I can try to measure the same thing for dusty galaxy and compare that to the correlation that's been found by Tacconi. So instead of asking, what are the mechanisms of star formation for dusty galaxy, then I ask is the dominant mechanism of star formation also distance stability for dusty galaxies? So I want to measure gas fraction and depletion time. To do that, I need redshifts for galaxies, I need gas mass, I need stellar mass, essentially these three criteria. So I designed a spectroscopy survey for that. This is a spectroscopy survey I designed and it's been carried out. It's based on SCUBA 2, by the way. It's a 850 micron selected sources. You have a uniform survey. You have 1,000 sources detected, and you follow that up with ALMA to pinpoint their locations. So you know exactly where the locations are for these galaxies. You have a few hundreds. Detecting lines are not very easy for dusty galaxies, so I picked the brightest ones. So these are the brightest sources. This is a histogram of the fluxes, and I picked the brightest 54. So I dump a lot of ALMA time in that. Essentially, a large program is just like 65 hours split into 2 cycles. Then I observed that. The one thing to know about this sample is that it's 100% complete. If you look at the original SCUBA 2 survey as well as the follow-up of the ALMA. So given the flux cut of 10 milli-Jansky, that's all there is in this field. You don't miss any of the sources. So that's what 100% complete means. The main goal is actually to measure redshift distributions. So I don't know if you see the curves here. These are predictions of redshifts. So this is 2, 1, 3. And some of the model predictions go, when they go brighter sources, they go lower redshifts. And some of the ones that go to the opposite. So one of the original goals is actually to test the redshift distribution. But for this talk, I'm going to focus on the gas fraction and gas depletion time. So this is the original pilot results of the 18 sources. You have lines. So each of them are spectra of the individual sources, but they are shifted to the rest frame frequency, given their redshifts. So the same band 3 observations, you're actually probing different frequency at the different redshift of the galaxies. And these are the location of each of the strong lines, CO lines, CO lines. So you get CO lines, you get a handle of molecular gas. That's the original 18. We have very high success rate, 95%. Just to give you a context of how hard it is to get spectra for dusty galaxies. People try using VLT and CAC. They dump 2 hours, 3 hours. The success rate is about 20 to 30%. And these sources about 1 hour per source. So they are very effective. And these are the galleries of the 455 galaxies, 54, sorry, galaxies. And again, the detection rate is pretty high. And their redshift is about 2 to 5. This gives you a sense about the quality of the spectra. It's not just blobs. They're actually very high quality of signal-to-noise ratio of more than 10. You even resolve the line, you see these double peaks maybe suggesting rotations. And you get sizes and all of that. I won't go into that in detail. In case you question, these are mid-J CO lines, but we also have follow-up of VLA and ALMA to get ground-based CO line transitions. So we get more robust gas mass estimates. In case you wonder, these are not the brightest strongly lensed sources. If you heard about the talks about very bright dusty galaxies, some of them are very strongly lensed. These are not. These are just blank field. They are not very strongly lensed. So when you try to understand their physical properties, you are not subject to the modeling of the gravitational lensing. So there's less uncertainties of their properties. So Zhenling, one of my students, now has moved to Leiden. He's done a tremendous work on modeling SCD. This just gives you a sense about the quality of the data we have. So these are the brightest source in the cosmos field. The cosmos field has a bunch of different data from X-ray all the way to radio. So we can model with the spectroscopy redshift, we can model with the SCD. These are the quality. A lot of band detections are here. When some of my colleagues doing nearby galaxy, they see this, wow, they say, well, you have more data points than we do in the local universe, in these bright galaxies. So this is the quality of, essentially our data and our sources. You do SCD modeling, you get robust dust masses and star formation rates. And you get gas masses in the CO. So here we go. So we got gas masses, stellar masses, star formation rate already. Now we are ready for the tests. So these two equations are Tacconi's equations. They're obvious. They're parameters of A, B, C, whatever that is. But all you need to remember is that what I plot is that I take that into account and plot in all the information I have: redshifts, delta main sequence, essentially offset from the main sequence, and stellar mass, and I'll get a predicted or so-called expected gas fraction and x-axis, right? But then in my measurement, I can also measure gas fractions myself, right? Because I have CO, I have gas mass, I have stellar mass. So I have my measurement of gas masses on the y-axis. So if they agree, they will lie on this one-to-one line, right? So here are the results. They sort of agree. They are slightly offset, but their slope is close to 1. So essentially, what you predict is what you get from the measurements, okay? They're slightly offset. We think that because of the alpha CO, the conversion factor from the CO to molecular gas. That's a factor of 4 here. I think the offset here is much smaller than the offset from alpha CO. So we think that we can claim it as consistent with the Tacconi's correlation. However, when you look at the depletion time, means the star formation rate efficiency, dusty galaxies, the y-axis is what we measured, and x-axis is what's predicted by the Tacconi relation. We found dusty galaxies are much more efficient in forming stars compared to the normal main sequence galaxies. That means that there's some mechanism other than distance stabilities that make the star formation more efficient in consuming gas and convert that to stellar mass. Okay? So this part, I conclude that there's comparable gas fractions relative to the typical star forming galaxies, but much more efficient in star formation rates. So then a question is that, maybe this question is that dusty galaxies, they are not all dominated by distance stabilities. They could be, they are not completely off. There's a slope. Maybe there's some of the galaxies that are distance stabilities. Some of the galaxies are actually mergers. So maybe they are a mixed bag of stuff. In this experiment, essentially, we can conclude that dusty galaxies are composed of things that not only the distance stability, they could be something else. Okay? So that's it for ALMA. Does anyone remember what I'm going to do next? JWST, I think it's Guangzhou. Here we go. Here we go. I'm sorry. Good. Someone pays attention. JWST. So one way to actually look at, if there are mergers of disks, just look at the morphology of these galaxies, right? So these galaxies, they look, by the look of it, you can see they're disks, they're mergers. But then also there are some quantitative ways, I call it Gini factors and M20 factors. You can sort of more or less separate them into mergers and non-mergers. So there are tests you can do. Previously, what you need to do is go to HST. HST is required for the resolution given the distance of these galaxies. Majority show the features of interactions. You see that tidal features, interactions, multiple groups, and that. But the biggest worry is that these galaxies are very dusty. And the reddest band of the HST only trace red-swim optical. So these lights are actually subject to obscurations of dust. So one cannot be sure these features you see are pure, genuine stellar distribution, or they are only the results of the obscuration of stellar lights in optical, right? Because you have patchy dust obscurations, then original disk, you can become a very fragmented, irregular galaxies. So that's the main worry. So the good thing about JWST, obviously, you go to the redder bands, so you probe deeper, less affected by dust. And then, here's just an example of a galaxy that looks like a merger or clumpy regular galaxies, but looks like perfectly spiral galaxies in JWST. So that again highlights the need for going to the JWST in order to get the true stellar distribution of these galaxies. All right, so people do that. They're excited about this. They collect a bunch of the images for dusty galaxies, because these are all in the UDS field, Cosmos field, those well-known fields. They have a lot of JWST data. And they just visually classify them. So they found, there are mergers, there are interactions, there are, grand design spiral disks, there are groups, and many other different things. So it's a mixed bag of different ways of disk and mergers. And that's sort of consistent with what we found in ALMA studies, right? So a very rough split of the merger and disk fractions, about 50-50, okay? But then when you look at the so-called the Thursday index, which is the light distribution of these galaxies, they are like disks. Thursday index of 1 is more like disk. In the higher values, you are more peaky in these distributions. And also the things I just told you about the Gini factors and M20, this is the line to divide mergers and the non-merger. Most of the dusty galaxies are located in the non-merger regime. So what's going on? I think the most likely situation is that these are still predominantly disks. They are in the process of dynamical interactions, but they are not in the final stage of major mergers where you have a very disturbed morphology, okay? So they're disks, they are minor mergers, and maybe tidal interactions, but they are not in the final stage of major merger. So that would be my explanations. So coming back to the original questions, how do we solve this? I think what we found is that they are neither disks, pure disks, or neither pure mergers. They are a mixed bag of disks, mergers, major mergers, and also maybe flybys and minor mergers. Okay. So coming back to these questions I want to address, I think it's a mixture of channels. As always, for the big debates, they are neither one of them. They are a mixed bag of the possibilities. Obviously, to make progress, we need a large sample to really pin down the exact fraction, right? So then that could be informative for the models to reproduce, hopefully. How much time do I still have? This is what? I got 10 minutes, roughly. All right, good. All right, future plan, the exciting part, JWST. So people know JWST is amazing. A full suite of instrumentation, spectroscopy, imaging, all the best qualities. Improve the resolution by order of magnitude, improve the depth by order of magnitudes. This is the difference you see. Thanks to Claude, make the slides. Very nice contrast of the ground-based imaging and the JWST imaging. You can really highlight the need of JWST to see and study the dusty galaxies. There are a lot of data coming in, and originally we started out with Adarsh, and now have Zhenkai and Claude. Our team is making custom pipelines to reduce JWST images, from archives, collect all the informations, and then we can make mosaics of the two fields for now. We have Cosmos and the UDS. There's a lot of things we can do. We also have mirror imaging. This is 7 micron and 18 micron, all that, all thanks to the great works of the Zhenkai and Claude and Adarsh. We can do a lot of science. One of the new science we could do is to search for lensed dusty galaxies that are faint before. So these are a few examples that were not discovered before. They are lensed galaxies. And then this is one of the known galaxy now. It's a ring galaxy that's been recently discovered. It's also a dusty galaxy. It's a foreground. It's Einstein ring. And these are two examples of the, these are red colors. They are dusty galaxies. They are strongly lensed. So we can use a uniform selection of dusty galaxies, and then we have a well-defined area. So we can just visually search. This is what Tinkai is doing, essentially. Visually search of these arcs and compute the fraction of the strongly lensed sources. As it turns out, this experiment is very powerful. You can plot flux densities. We can roughly know their flux densities. And the y-axis will be the strongly lensed fraction, well, number counts of the strongly lensed sources as shown in the blue. And this is the total number counts. We can constrain the number counts of strongly lensed sources. And this actually, in turn, can help constrain the statistical property of the foreground mass distributions. Okay? So that's one new science case that I could enable for this data. And now, not only that, now we have a lot of project going on led by the team members. And then, obviously, JWST, everybody's interested in that. So we have, we'll, essentially request that to join the consortium, essentially. Now we have a consortium, started from our own group, but now expanded to people from local universities as well as international collaborators. And there are, almost a dozen projects going on. So if you're interested, feel free to talk to any of us. We'll come to join the projects and make use of the JWST data. Next one, I promised to speak about the next generation submillimeter telescope. It's called ALMA. It's a 50-meter dish, and it's going to be hopefully built in somewhere in Atacama Desert, somewhere next to ALMA. Hopefully, pick a nice site. I mean, Satoki knows more detail about the location. We're going to cover a wide wavelength range from essentially 0.3 millimeter to 3 millimeter. There's a lot of instrumentations, multi-crowd imaging camera, and also IFU, also heterodyne focal plane. You're going to feel the focal plane of this 50-meter dish telescope. We're going to have millions of heterodyne pixels to do that. This is the next generation. This is the goal, the dream, right? You're allowed to dream. And also very wideband single beam heterodyne receiver you can do a lot of science with. The initial phase of the design study has finished this year, but the good news is that the next funding has come in that's been approved for the next 3 years. So, I mean, it's likely we're going to see this project being more advanced by 2028. There's a lot of science cases. I'm not going to go through all of them. I'm just going to focus on extragalactic. This is the predicted imaging of a 50-meter dish. This is one of the so-called confusion limited, where it's very poor resolutions. You dump enough, however long exposure time, you cannot go deeper. And the right-hand side is essentially, you probably won't hit the confusion limit. It's got very high resolution because it's got a 50-meter dish. We have predictions for this redshift stop emission rates. There are multiple curves showcasing essentially the current limits of each individual experiment. This is ALMA, 350 micron, ALMA 3 millimeter, and Herschel is right here. And all of these experiments, they don't probe the L star, essentially the knee of the luminosity function, which is shown in this black curve here. They don't probe that deep enough. With the design of the ALAST, with the 8 bands, with 1,000 square degree, you put in 1,000 hours, you're going to detect galaxies as above the knee all the way to redshift 6, right? So you're going to have millions of dusty galaxies. This is the number that's almost like Sloan kind of stuff. It's something that we cannot dream of now. We have 1,000 roughly, but with this next generation, we're going to have millions. What kind of science cases we can do with this? One of the most fundamental questions about this star-penetrating density again. How much of the star-penetrating density are actually in obscure star-forming regions? And currently, we have good constraints up to redshift 2, but above redshift 2, and it has very limited amount of constraints, as you see in the red points here. So we're going to actually, with this survey, we're going to essentially solve these problems all the way to, I guess, redshift 10. We can build this, essentially the density curves all the way to e power to the reionization. Okay, so we're going to do that. If you're interested in dust properties of galaxies, because it's multi-band surveys, 8 bands in total. So some of the, a lot of galaxies are going to have at least 3 or 4 bands, and some of them are going to have 8 bands detections. This is the prediction of how tight you can get for dust masses. This is the luminosity this scatter. This 0.2 dex is 50%. It's much less than 50%, maybe 10% for the luminosity, but about 50% precision for the dust masses. You have a very good map of SCD. You have a very good constraint of the dust mass. You can look at the things like emissivity index for dusts. You can look at dust temperatures and all things that you can do. You can build dust mass functions, however you like. You're gonna make solve these problems all at once. What I'm most excited about is a spectroscopy survey. Obviously, we're not going to get millions of galaxies that spec Zs because you need to get spectra. But then we still can get about 100,000 with about 1 square degree. You have 3,000 hours. You can use that with IFU. You can detect that. That's 100 times more than the spec Z we have. Why am I excited about this? I think I'm running out of time. I'm just going to quickly go over. We can do cosmology and try to address Hubble tension. We're going to expand the BAO measurements beyond the current redshift limit, which is about 2.5. You see this new release. David Schlegel just visited not too long ago. Showed this plot. You have BAO measurements and constraints of cosmological parameters. Using spectroscopy surveys up to about redshift 2.5. And with PFS, you probably have reached that limit as well. Funny enough, dusty galaxies, they only start to pick up at redshift 2 and beyond. So you have a galaxy population sample that's predominantly at the high redshifts, okay? Not at the low redshift like optical telescopes. So you can do that. We can do spectroscopy surveys. We can, in principle, push the cosmological constraint with the spectroscopy surveys, but beyond redshift 2.5. Very quickly, we try to make forecasts with the student pursuing from Tsinghua. Obviously, we don't have a mock galaxy simulations where we use pure dark matter only simulation box of redshift 3. It's wide enough, 2 gigaparsec minus h, and Planck cosmology is fiducial, and purposefully select halos between 12.5 and 13.5. This is the halo mass based on our current statistics that estimates they are residing at this halo mass range. They are massive ones compared to the Lyman-Bray galaxies and emitters, which are about 10 to the 12 and 10 to the 11s. These are very massive halos. So you have better bias measurements and complementary to the low mass galaxy surveys. And she has done an amazing job of full shape analysis, fittings of the BAO features, also in monopole and quadrupole features. I cannot go into detail, but the basic message is that we can constrain in this pure mock dark matter only simulation, we can constrain the Hubble constant to 3% roughly, that level. So the hope is that with dusty galaxy survey, we can push the cosmological constraint to high redshifts. Obviously, we use redshift 3 as a test. We can expand that to high redshifts. And obviously, the next steps will be to use a real mock galaxy catalogs to run the forecasts instead of dark matter only. Okay. So coming back to this, next plan will be exploit JWST and help plan at last. Last but not least, in the 5 years, I really much appreciate the funding that's given by the Sinica and NSTC. And front office staffs, I want to really appreciate their efforts. I mean, getting funding is one thing. Managing your money is another. I mean, front office staff is really helping a lot. So whenever I go to front office, I can just say, "Oh, I want to do this. Can I do that?" And they'll just go figure it out. Yeah, you have enough money. You can do it, right? If without them, I have to figure it out. Do the accountings myself. And I think that's easily half of FT or whatever, 10% of FTE of my time. So they're awesome, and IT staffs are awesome. I also want to thank all the mentors I have, faculty mentors, and also the students and postdocs I've worked with over the past 5 years. Thank you. With that.
Okay, questions for TC?
Two questions. First, the second part.
Mm-hmm.
The final conclusion was that the
Discs.
Sorry,
Yeah, telescope dish.
disk and the mergers. But at the introductory part, that those kind of hazy galaxies,
Mm-hmm.
that the merger doesn't boom up the SFR, only a factor, nothing older.
That's right. Yeah.
Is it consistent with
Yeah.
that story?
Yeah, I think so. So I mean, I guess the thing is that without boosting, this galaxy can already have hundreds of solar mass per year. But then with mergers itself, they can also boost up to a few factors, but that's still a few hundreds, right? In the local galaxies, if you don't have mergers, you have a few of solar mass per year. You cannot make it to a dusty galaxy, but you have to have mergers to do that. So I think that makes sense. If a disky galaxy can already make a lot of stars, and that makes a lot of dust already.
And related to that, you show the ALMA image, which is not that great resolution, but the SUMMA result. Can you actually calculate the turmeric Q instability values? Probably very roughly. But
Oh yes. Sorry.
and actually, it was
You mean using ALMA
ALMA.
continuum?
No. Because turmeric Q.
Yeah, you have to
need
have gas. Yeah.
Velocity
Yeah.
information.
Yeah, velocity information.
Actually, actual calculation. Of
Yes.
Q instability.
So I mean, I don't have a map here, but people do that, and then I think it's below 1. So that's essentially suggesting it's unstable disks.
Okay.
Yeah, it's maybe about 0.5, 0.6. Yeah.
Okay, other questions?
In case you move to a slightly shorter wavelength in infrared, like 160 or 100 micron, what happens to the number density of galaxies? Because you talked about 450 and longer wavelength.
Mm-hmm.
So in case of star formation heating up the dust, we expect warm dust emission, right?
For if you have, you mean if you go to shorter wavebands,
Shorter wavelength infrared.
the mid-infrared,
Yeah.
far infrared, 100 micron you said. And then what's the question again?
What happens to the number density of galaxies? Do you boost up the cosmic star formation rate density when you consider that band and count all the galaxies? Or you catch up all the galaxies which you see in the longer wavelengths?
So normally, when you go to shorter wavebands, you probe dusty galaxies are actually slightly smaller redshifts. They are lower redshifts. So, so I don't think that. So I don't fully understand the question. You are asking if you count for 100 micron sources, and then does that include it in the soft moisture density?
Yeah, so
Yeah.
if you consider 100 micron image, do you see any source which is missing?
Oh no, normally no. So the other way around. Usually the longer waveband sources are missed in the short bands because the longer waveband sources are probing higher redshifts. And then you don't normally see that in the detection limit of the shorter wavebands. Yeah. So which is why I think up to redshift 2, the soft moisture density is already mostly resolved by like Spitzer or Herschel because they are observing shorter wavebands. You picked up most of the dusty galaxies at the lower redshifts. But the question is the longer redshift one, higher redshift sources. Yeah.
Ida, you have a question? So in the third part, could you tell us more about how you plan to measure the dust emissivity index with ALMA data?
Oh, for my plan, I'm just going to use the single black body. I'm sure you not agree, but that's what we do now. But then obviously you have more data points, you can have multiple components, right? I mean, once you have the data, you can feel free to play around with whatever you want. That's what I did. I mean, I just do a single component. And then to be fair, for dust emissivity index, I don't think that changed things much, right? With the 2 component or single component.
Well, the problem is, so
Right. Yeah, I guess that's always going to be there, no? But I guess you have long bands, then you could constrain beta well. And then once you can constrain beta well, then you can constrain mass well, no?
Yeah, the mass is derived with emissivity index.
Right, but then if you have data to constrain the emissivity index, then that should break the degeneracy.
That is degenerate also with the temperature, so there are three things.
That's right, so you have to have redshifts for these galaxies. And you have to have map of both sides of the peak. But I agree, and it's model dependent, whether it's optically thin, optically thick, multiple component. But I guess the point is, at that point, it's model limited. It's not data limited, because the data is what you're going to get. You have A bands, and it just depends on how you're going to model the dust.
Wait, sorry, is the emissivity index you mean beta?
Is it not what you meant? What you meant?
I mean, I was.
Dust emissivity index.
Kappa, actually, emissivity.
Oh, that's opacity index, dude. Kappa 0. No, there's no hope.
Okay.
You gotta assume Milky Way. It's like what everybody does, right?
I'm just curious, how many galaxies do you need to get the BL signal?
Ha! We have 800,000 here in the simulation. I don't think we're gonna get that in real life. So we're probably not gonna get 3%, but then I guess you can put constraints. And they have higher bias, so I hope we can still be competitive to LBGs and LEs and David Lego.
Yeah, but you said on one of the pages you said 1,000 hours are required for like, so 3,000 hours are required
Yeah.
for 3 degrees.
Yeah.
And that's
100,000.
yeah, so
So we're not going to get 800,000, probably not. And I mean, this is a very ballpark number, I would say, but it just estimates. And also, it's 100,000 split into across redshift range. So I guess if you have given redshift range, you may be about, I don't know, a few tenths of thousands only. But this is essentially the first step. I mean, there's a long way to go. We don't know the performance of the instrumentation yet. So very rough.
short question. For AS2 prospect survey,
Mhm.
you see diversity in the spectral emission lines profiles. I find it very interesting there. I was wondering if we checked the images for these kind of objects at these kind of very large velocities, even double peak, multiple peak profiles, may be indicative of ongoing kinematic process for the galaxy.
Yeah. So that's surely next step. I think we've looked into that. And indeed, some of them actually appears to be merger, very clear two nuclei, but some of them are still disks. Because double horn doesn't mean they're merger or disks, because they just means they're rotation. It could be, there are two galaxies going this way, and there could be a disk that are having this rotation. So I couldn't tell. But then, the fact that the two peaks are not symmetric, that probably means something.
It sounds like we have it could be one systematic way. And you said this is only 1 hour?
Yeah.
Which is much cheaper than optical
Yeah.
surveys
Yeah.
that are needed, like IFUs.
Mm-hmm.
So I feel like, this may be really.
Yeah, so one obvious next step is to go high resolution. So these are poor resolution, 3 arcsecond. So go high res, do the dynamics. Yeah.
You can survey.
Yeah.
You
Yeah.
can trade merger fraction maybe.
Yeah, that's one surely something we can do.
I have a question about your scuba to survey the lensing cluster field. So I don't fully understand how the confusion limit work, but wouldn't you in the strongly lensing field, wouldn't you also magnify the background small sources that are causing the confusion? So you make all the So most of the dusty galaxies are behind the clusters. You make everything brighter, and when you do that, you also have much more detectable sources that contribute to the confusion levels. So I guess I was wondering why the actual detection limit can go down when you also have many.
Well, you still have the confusion at the image plane.
Yeah.
But then once you demagnify that to the source plane, you're supposed to see a fainter fluxes. So you still have confusion at the image plane, that's for sure. But then once you model that back to the source plane, everything just goes fainter. Does that make sense?
Okay, I'm not sure.
Yeah.
Do you have other questions for TC? If not, we can continue the discussion outside. And let's thanks TC again.
Thank you.